This week on the Tech ONTAP podcast, Kim Garriott joins us to talk to us all about digital pathology.
Welcome to the Tech ONTAP podcast with Justin Parisi.
I love NetApp. Oh, yeah. NetApp. I love this company. Support.
I love NetApp because it's so fun.
Hello and welcome to the Tech ONTAP podcast. My name is Justin Parisi. I'm here in the basement of my house, and with me today, on the phone, we have Kim Garriott. So, Kim, what do you do here at NetApp? How do we reach you?
Hi, Justin. I am the Chief Innovation Officer of our NetApp Healthcare and Life Sciences practice, and also the General Manager for Medical Imaging. And you can reach me at kim.garriott at netapp.com.
All right. Excellent. So Kim is here today. She's been on the podcast before to talk about healthcare and medical imaging and that sort of thing. Today, we're going to talk about something new, something that's kind of cutting edge in the industry, and that is a concept known as digital pathology. So, Kim, could you please tell me what that is? Because I don't know what that is, and I'm sure a lot of people haven't heard of this before other than, what the words mean, right?
Yeah, no, exactly. It's a really exciting field that is coming to life in healthcare and life sciences, and had some interaction with pathology. So any kind of tissue removed from your body, say you had a gallbladder removed, or you went to the dermatologist because there's a little mole or a bump on your arm, and they do a little biopsy sample of that tissue or fluid from your body is set on a glass slide. And then that glass slide is put under a microscope, and a medical professional called a pathologist looks at the cells and the tissue on that slide and makes a diagnosis, most commonly that we can relate to, is whether that skin tissue is benign or malignant, whether you have cancer or not, or the type of cancer that you may have. So digital pathology is really the next digital frontier in clinical medicine, and maybe the last major clinical workflow to go through a digital transformation. And that's when we take this glass slide and we digitize the slide so that the cells become an image, and then the pathologist can look at that through their computer versus looking at the glass slide through a microscope. So digital pathology, by definition, is a dynamic image-based environment that enables the acquisition, the management, and interpretation of pathology information that's generated by digitizing that glass slide.
So it seems like such a simple concept, right? Like taking a glass slide and turning it into a picture. So I can't imagine it's that simple. What is involved with digitally creating an image of these slides? Is it as simple as scanning in a machine, or what else is involved? Is there any AI, ML impact there?
It is a complex process. However, there are huge advantages over how we look at those glass slides on a microscope today. So we would have the same process of actually putting the tissue sample on the slide and staining the slide, or applying a chemical to the slide to make certain cells be more visible than others. But then we will take that slide and you put them in trays. And these trays can hold anywhere from one slide to hundreds of slides. And then you place them in a device or a whole slide scanner. And then each slide is then individually scanned. And there's different ways to scan the slides depending on the type of sample that is on the slide that you're trying to digitize. So you can do tiling, where the scanner takes little tiny squares of images in a row, or like they'll do tile strips all at once, where it's just one linear read of data. Or we can actually, for some types of tissue samples, we want to be able to have that X and that Y plane scanned, but we also want to have the view through the cells, because you can imagine on a glass slide, when you put the tissue on there, it's not all flat. It's not, the cells don't line up all into one plane, right? So there's multiple planes or cells that can be stacked on each other as you look down through a sample. So that type of Z-stack scanning, an intense scanning process that gives us a really good depth and allows us to see through that tissue. So once the slide is scanned, then those images will then present on a viewer for a pathologist to look at. Now, that's the simplest workflow. Where the dynamics really come in and where we can really enhance our ability to provide precision medicine to patients, meaning individualized diagnosis based on their condition and their sample alone, is when we apply AI to this. We have a lot of improvements that will come in this field because of the ability to help the pathologist do their job. That's kind of the first side of it. So what do I mean by that? Today, when a pathologist has a glass slide and they put that slide into the microscope, they have to first identify what's the area of interest that I want to look at. What is it on this slide sample where the cells that I'm interested in are clustered on? So first I have to identify that. And oftentimes they take just a marker and they literally write on the glass. And think about how small those glass slides are, right? You remember when you were in biology or chemistry, how small those slides are. So a pathologist has to take a marker and mark around that and then identify the cells of interest and then count individual cells, which is very time consuming for a pathologist. So at the front of the workflow, we are working to develop AI models to mark the area or the region of interest for the pathologist and begin to do the cell segmentation or the cell counting so the pathologist can really focus on identifying the types of cells and the behavior of the cells versus just simply prepping the data, if you will, for them to look at. And then beyond that, AI, and we have lots of AI developers, as you can imagine, that are working on solutions or AI algos or algorithms to be able to help look at the cells, identify the cells that are interesting, and then compare those cells to databases of millions of other similar samples and be able to improve that precision medicine diagnosis. For instance, today, we only have one approved AI algorithm in the field of pathology for disease detection, and that is comparing tissue patterns from a needle core biopsy used in prostate testing. And we're able to take that needle core biopsy sample, compare it to a large database of known cancers. And in the clinical trials for this AI model, they reduced the occurrence of false negatives. That means I don't think I see any disease here. We have reduced the false negatives by 70%. So that means 70% of the test cases that were used in these clinical trials actually had cancer present, but the human pathologist by themselves did not diagnose that. So 70% of the time, a patient had something questionable or wrong with them that we did not detect. So by applying AI, we can be much smarter about our diagnosis because we're comparing it against millions of other tissue samples that may be similar. And in this example, we can see how that really can impact lives. Now, I'm not saying that 70% of false negatives, that those people had a critical condition, right? But that could be someone that an early intervention could keep them from becoming sick, or maybe there's other things that we can do for that patient to help them have a great quality of life and not actually be negatively impacted by the disease state that may be occurring in their body. And that's the beauty of precision medicine. That's the beauty of how we can apply AI and make a difference in healthcare and in patient diagnosis.
Yeah, another benefit of doing this is, so that these slides, I don't know if you've ever worked with any glass slides. And I remember in high school doing the biology stuff, those things are real fragile, right? So they break pretty easily. And then you have to think about also the organic material itself. Over time, it breaks down. So having images taken of that really reduces the amount of worry about losing this valuable data that you've had. You no longer are storing it as a hard piece of evidence. You're using digital imaging, which can last essentially forever.
Yeah, that's a great point, Justin. And that's another huge benefit of this digitization of these whole slide images. We use glass slides in a manner of ways. One is for primary diagnosis. The second is gaining a second opinion, right? I want another pathologist to look at this image or to look at this tissue to see if the diagnosis matches the first pathologist that looked at it. And then we also have research and education where these samples are very important. So as you can imagine, a lot of slides get broken, like you just alluded to. And by digitizing these images, we're able to easily share the image, where in the past, if we needed a second opinion, we would have to box that glass slide up and send it by courier to another pathologist, which can take days, which is a delay in diagnosis. And what if that slide gets broken? What if it gets misplaced? So not only the time consideration of transferring that physical content to another provider, it's also the time to diagnosis. And if you are waiting on a cancer diagnosis, days matter, right? We know that. So by being able to communicate with a digital form of the tissue, then we are able to reduce the time to diagnosis, be able to keep that sample. And then also, if you look at use cases with research and education, as students are sitting in a classroom, you want them all to be able to see the same interesting case. And today, you have to pass this glass slide around to students or hope that you had enough tissue sample that you could make a number of glass slides out of it. But I think it's pretty easy to see in this way that if you have that tissue sample digitized, then every student can look at that same sample at the same time and be able to really improve the education process. And, we don't have to, again, worry about breakage, because once it breaks, then the tissue samples are stored and no one can use it. The other thing about the glass slides is that they are very heavy, if you can, imagine that. And today, organizations have to retain those physical glass slides for years and years and years. And that's a lot of real estate to have to be able to maintain these slides. And I heard a statistic that Iron Mountain has kind of well over 1 billion of these glass slides that organizations are having to retain, but they never go back and look at them, or very, very seldom for primary diagnosis do you go back and look at them, but they have to retain them, and that takes a lot of space. I'll give you a couple of interesting statistics. So there's one large academic medical center here in the US that started scanning their glass slides a few years ago, and they have scanned almost 3 million slides. And just to put that in perspective for you, a medium-sized hospital probably has about 100,000 pathology studies a year on their patients. So that would be, 100,000 glass slides. This organization has scanned 3 million, almost 3 million slides. That turned out to be around 3 petabytes of data. But to the point of the weight of the glass, it's 17 tons of glass slides that were scanned. And they estimated that if you were to stack those slides on top of each other, it would be 1,155 stories of slides, approximately. So that kind of just paints a picture of the size of these glass slides. And if we're able to digitize that, that really takes a burden off of the healthcare organization or off the life sciences organization that may have to retain that very heavy.
Yeah, it sounds like slides are kind of like the tape of the healthcare industry, right? Like trying to get away from that, right? So with slides, I guess this would kind of spawn some innovation as well, because you start to think, okay, why am I putting all this stuff on individual slides?
Where we're going ultimately is lots of smart people are working on technology so that the glass slides go away eventually altogether, and that we're actually able to use the technology. And there's, several different ideas that people are pursuing. But one idea is with something called a micro CAT scan. So today we have big CAT scans or CT scanners that you need to have a certain part of your body scanned for better imaging. We're all maybe familiar with that, or have family members have one of those. We have small CT scanners now that can sit on a countertop, and the tissue sample itself without the slide can be scanned by these micro CT scanners. And so from the original acquisition of the data, it's in a digital format. And this is very similar to the early days of radiology, where we would shoot a chest x-ray and then we would still have film, and we would put that film in a cartridge, and then we would load that cartridge into a digitizer, and then it would digitally be scanned, and out comes this digital chest x-ray. So I liken the cartridge to the glass slide today. And now when you have a chest x-ray, you simply go into a digital radiology room. You still stand in front of a sensor. They shoot the x-ray image of you, but it's completely digital in format now from the point of acquisition. So from the point of acquisition for pathology samples in the future, they will be digitized versus having to have this interim medium of glass for the tissue to be adhered to. So that's where we're ultimately going.
I figured we wouldn't just keep doing the same thing over and over again, because that does seem very time consuming, very wasteful. And there are probably better ways of doing this sort of thing that people are going to come up with. I'm not someone who's going to come up with that idea, obviously, but with my wipe off the slide idea, right?
Right. No, but
just get some Clorox wipes. It's fine.
But it's like, why can't we repurpose that type of thing? And for most of us, we don't understand the process, so why wouldn't we?
Yeah. I mean,
I do think it's really important. The evolution that will get us to this digital age is really important. And it's some super cool technology to see what individuals and organizations are working on to move this field forward.
When you say things like petabytes of data and, needing a place to put all that, I immediately think, okay, well, where does NetApp fit in, right? I mean, this sounds like a very lucrative way for NetApp to get involved, because we, of course, have multiple petabytes to put things, right? So where does NetApp fit into all this? Are you looking at on-prem storage? We're looking at cloud storage, a little of both. How is the industry moving towards this?
Before I answer that question, let me put this in perspective of what the impact to healthcare is from a health IT perspective and the data management that's going to be required for this whole slide imaging. So we talked about the chest x-ray a second ago, and it's a really great example to compare. So a chest x-ray, normally you get one or two views of that image. It's very straightforward, single image or maybe two images, unlike an MRI or a CT where you could have hundreds of images that make up a single radiology exam. So a chest x-ray, one single image, it's the highest resolution image that we have in radiology. And it is approximately 10 to 15 megabytes for one radiology chest x-ray image. When we look at digital pathology and whole slide imaging, a single image, and will be multiple images within a single case or exam, one whole slide image is approximately 1.5 to 3 gigabytes in size. So we can see that comparison of the highest resolution, densest pixel image in radiology today is 10 to 15 megabytes. We'll jump to 1.5 gigabytes for a single pathology image. So CIOs know that their organizations are starting to think about how do they begin to take this digital transformation journey in pathology. And from a CIO perspective, how are they going to manage all of this massive data? Because today, it's widely accepted that medical imaging comprises 80% of all clinical data generated worldwide. Well, that number, with the addition of digital pathology, is set to explode. So if a medium-sized community hospital that's generating 100,000 pathology cases a year is just average, right? That organization is looking at probably 500 terabytes of data that's going to be generated annually, and that's net new data. Helping organizations understand how to prepare for this new massive volume of data that's coming their way, as well as be able to think about strategies to leverage the value of that data in the use of AI model development or in the use of research and education is a really great place for NetApp to be. And whether an organization is looking to manage this data completely on premises, because we do still have some hesitation to putting masses of data in the cloud from a healthcare perspective, whether that's from a privacy and security perspective, or maybe there's concerns about the egress fees if we do need to bring that data down from the cloud. So whatever the reason, if an organization wants to stay on-prem, we certainly have great technologies to help manage that data, whether it's in that file format as its initial type of data retention, or you want to promote that data to a more cost-effective object storage, perhaps using StorageGrid and using NetApp Fabric tools to manage the tiering on-prem. Or if you are more cloud comfortable, our technologies can help you have that best hybrid experience by being able to leverage our NetApp ONTAP operating system across any of the public cloud providers. And it's going to be really advantageous and beneficial to the patient population for organizations to be able to have their clinical data as part of the AI algorithm development process, or that AI model training or machine learning model development. So organizations that are wanting to leverage the value of their data in that way, in a totally anonymized way that protects patient identity and patient privacy, of course. By leveraging NetApp technologies, we can help organizations to replicate that information to the cloud in a secure way.
We've talked about how NetApp fits in here and what sort of things digital pathology brings to the industry. What about if I want to learn more about this? Like, where would I go to find more information about digital pathology, NetApp solutions?
Yeah, we have a great amount of information out there, Justin, that we'll include the link in this podcast, and then you can always find this information at netapp.com. One thing that I did want to add, and one thing that we have information about that I think is exciting and really timely for this field, is a partnership with Google Cloud that was announced at the beginning of October. And this is the Google Cloud Medical Imaging Suite, of which NetApp is a core component of. And with the Google Cloud Medical Imaging Suite, we're able to replicate data volumes from on-premise, whether that's an entire data set or perhaps a data cohort, replicate that data into the Google Cloud, into a Cloud Volumes ONTAP instance or Cloud Volume Services instance. And leveraging technologies like Cloud Data Sense, we're able to help customers very quickly be able to categorize and map the data that's contained within the medical image, or in this case, a whole slide image, so that they can easily be able to audit the data, but also in this use case, most importantly, be able to query the data and create specific AI data cohorts that then feed into this greater AI model development environment within the Google Cloud that provides a robust set of tools to help customers be able to partner with third-party AI developers in secure ways so that those developers do not have to actually be accessing the data on site. So by leveraging this Google Medical Imaging Suite, we are able to bring the power of NetApp technologies, partner with Google to provide a rich set of AI development tools and services for customers to be able to take their pathology data to the next level.
Sounds like we got a good start on this burgeoning industry, right? Like, it's not quite at the level of a medical imaging, but it is getting there, right? It's the future of pathology there. So Kim, again, if we wanted to reach you, how do we do that?
Yep, you can simply reach me at kim.garriott@netapp.com.
All right, that music tells me it's time to go. If you'd like to get in touch with us, send us an email to podcast@netapp.com or send us a tweet at NetApp. As always, if you'd like to subscribe, find us on iTunes, Spotify, Google Play, iHeartRadio, SoundCloud, Stitcher, or via TechOnTapPodcast.com. If you like the show today, leave us a review. On behalf of the entire Tech on Tap podcast team, I'd like to thank Kim Garriott for joining us today. As always, thanks for listening. Oh, yeah.
Is it just me that's getting off on this?
Oh, yeah.